These are the notes for AP Calculus on the topic of the area between curves. So if we want to find the area of a region enclosed between two curves, there's two different ways you can go about it. You can use a vertical rectangle, dx, or a horizontal rectangle with dy here. So let's see what that looks like graphically and then see how it's set up. So it says here, if f of x is above g of x on the interval from a to b, then the area between the two curves on the integral is the integral from a to b, and then f of x minus g of x dx. So what that would look like is within the region, f of x is the one that's above g of x. So if this is f of x, and this is g of x, then again, dx here represents the width of our rectangle, which in reality is infinitely thin, but we can't draw it like that, so we just try to draw a thin rectangle like this. And dx means an infinitesimally small change in x, so that's our width there, right there. And then to get the height of the rectangle, notice you'd have to take the difference of f of x minus g of f of x first, because it has a bigger y coordinate. So f of x is the one that's on the top, minus g of x is the one that's on the bottom. So when you take f of x minus g of x, that's what gives you the height of your rectangle. And then you integrate all those infinitely thin rectangles starting from here all the way to here. So what you use, since it's all in terms of x, is the x coordinate. So the lower limit a represents the x coordinate of this point. And, oops, not b there. I'll call this one AC, and this one BD, because we're just using the x coordinates from a to b here. Starting with the lower limit, because it's further to the left, has a smaller x value, and then b has a bigger x value. So integrate all those from a to b, and that's what gives you by integrating, by adding up all those infinitely thin rectangles, those areas, that gives you the exact area of the region enclosed. So that's the more common way to do it, but sometimes it might be easier or necessary to instead use a horizontal rectangle and to find the area. Instead, make your integral all in terms of y. This time, f of x is to the right, f of y is to the right of g of y. So it looks something like this. If this is f of y in our region and g of y, there's our region enclosed. So now when you draw the rectangle, this time the width right here is dy. It's a change in the y coordinate, infinitesimally small change. So that's still the width. But now to get the height, which in this case is sideways here, you'd have to take the one furthest to the right, which is f of y, minus the one furthest to the left. The one furthest to the right goes first because that has a bigger x coordinate. So now you would go the right minus the left. And here's the height. So this time, though, since it's all in terms of y, you'd have to use the y coordinates of these points. So here, because this has a lower y coordinate, it would go first, so its y coordinate, you could write this point is the point dA. So a would be the lower limit here, a would be the y coordinate. And then here, if this is CB, b is the y coordinate of this point. It becomes your upper limit. So here the whole integral is in terms of y. These are the y coordinates, a to b, and then on this one the whole integral is in terms of x, and these are the x coordinates. So let's see how this works on some example problems now. So the first one here, and this is supposed to be touching the x-axis, there's just a little gap there that shouldn't be there. And then, so we've got the region in the first quadrant, so it's in the first quadrant here, whoops. Bounded by the graph of y equals square root of x minus 1. So you can see that's the half parabola here. and the curve y equals 7 minus x. That's our linear one right here. So it says write an integral in terms of x that gives the area of R, then evaluate to find the area, and then write an integral in terms of y that gives the area of R, then evaluate the integral. So let's do both of those. So in terms of x, let's draw a representative rectangle vertical with dx. But notice when you do that, the rectangle here is between the square root of x minus 1 and the x-axis. But right here, notice that actually changes there. The curve on the bottom is still the x-axis, but the curve on the top changes to 7 minus x. So because of that, this would require actually two integrals. But in order to figure out where they start and stop, we'll need to figure out these different points here. So let's figure out where this one intersects the x-axis. And when it's an x-intercept, you know y has to be 0. So if you just look right here and see what would make y 0, you can see that would be 1. That's 0.10. And you can do a similar thing for the 7 minus x, the first x-intercept. We know the y-coordinate has to be 0. And what would make y 0 here would be if x is 7. Next, let's find the point of intersection between the two. Right here. In order to find that, you can set the equations equal to each other. In other words, you're really just using substitution. You're substituting this, which y equals, in for the y right there. Or you can do vice versa. So we'll have the square root of x minus 1 equals 7 minus x. And then to solve this one, you would first square both sides to get rid of the square root. So that would cancel out the square root and you get x minus 1. And on the right side, that's like 7 minus x times another 7 minus x. So that would give you negative x and negative x multiplied by positive x squared. Then we'd have two negative 7x's, which combined to be negative 14x. And then 7 times 7 is 49. And then to solve it, you can get one side equal to 0 here. Since the x squared is positive, let's get the left side equal to 0 by subtracting x and adding 1. So then we'll have 0 equals x squared, negative 14x minus x, negative 15x. Negative 49 plus 1 is 50. And then factors of 50 that add to be negative 15 would be negative 5 and negative 10. So initially it looks like we have two possible x coordinates for our points of intersection. X equals 5 and x equals 10. But if you look at the graph, you can see the x coordinate right here is 1, the x coordinate right here is 7. So we know this has to be somewhere between 1 and 7. So 10 does not make any sense. The reason why we're getting 10 is because the way we solved it, when we squared this square root of x minus 1 that gave us a half parabola, that actually changed the equation to be a whole parabola. So it actually curved down like this. And if you curve it down like this linear one would eventually intersect again a second time with the graph, and it would intersect right at x equals 10. But for our problem, that's not relevant. It's x equals 5. And then to get the y coordinate, all you have to do is substitute in 5 into either equation. They should be the same since this is where they intersect. So if you substitute 5 in here for x, you get 4. Square root of 4 is 2. Or you can substitute 5 in here for x. 7 minus 5 is also 2. So you get 5, 2 is our point of intersection. So on this one, now to integrate, this first region with the first rectangle will be the integral from the lower limit is the x coordinate. This is in terms of x, which is 1. And we integrate this all the way until this dotted blue line where the x coordinate is 5. So we'll set up an integral for just that region. And that would be the square root of x minus 1 minus, here is just y equals 0. This is the x-axis. So you just subtract 0, which doesn't change anything, and then times dx. That would give us the area up until the dotted blue line. And then to find the area from the dotted blue line to this x-intercept, you'd have to add another integral. This time the lower limit would start at the x-coordinate here, 5, and stop at this x-coordinate of 7. And this one would be the top minus the bottom. In this case, the top one is 7 minus x. Minus, again, the bottom one is 0, so that's not going to change anything there. So that would give us the area of this region, this triangle right here. From the dotted blue line to there. So adding those up would give us the total area. So let's go ahead and that's setting up the integral, right, in terms of x to give the area. Then sometimes we'll ask you to set up, sometimes actually evaluate. So let's evaluate this. So this one you could think of as square root of x, sorry, x minus 1 to the 1/2. And then you can use u substitution or setting u equal to x minus 1. Or this one you can use as a shortcut because the derivative of x minus 1, the function size, is just a constant of 1. So when you integrate that, if you use the shortcut, that would just become x minus 1, add 1 to x, add 1 to 1/2, gives you 3/2. Divided by 3/2 is the same as multiplying by 2/3. Evaluate from 1 to 5. And then let's go ahead and integrate this one. And when you integrate this one, since they're just subtracted, you can each one separately. So the integral of 7 would be 7x minus integral of x would be x squared over 2. And this one's evaluated from 5 to 7. And then let's go ahead and simplify this. You can pull the 2/3 out in front on this one. That's a constant. And then you can also rewrite it in radical form. So instead of x minus 1 to the 3/2, that's the same as the square root of x minus 1 cubed. And since we didn't use traditional u substitution, just normal u substitution, that's why we kept the lower limits 1 and 5. Lower and upper limits. And then plus on this one, you would substitute in the 7 first. Times 7 would give you 49. Minus 7 squared is 49 over 2. And then minus this whole thing, when you substitute in 5, 7 times 5 is 35, minus 5 squared, 25 over 2. Now let's go ahead and substitute into this one. So we'll have 2/3 on the outside. And then when you substitute in 5, that's 5 minus 1, 4. Square root of 4 is 2. 2 cubed is 8. Minus, when you substitute in 1, that gives you 0. And let's go ahead and start to combine on this side. So you could subtract 49 and 49 over 2. Or notice it might be easier to just combine the ones that have the same denominator already. I'll combine the integers first. 49 minus 35 is 14. And negative 49 over 2 plus, because the negatives cancel out here when you distribute the negative, plus 25 over 2 is negative 24 over 2. So 2/3 times 8 gives you 16/3. And then if you combine these, well, 24 over 2 is the same as 12. 14 minus 12 is 2, which is the same as 6/3. Add those up gives you 22/3. And this is area. So there's not specific units here, but if you did have them, it would just be units, whatever they are, inches, meters, whatever it is, squared. So we get 22/3 for the area. That's using, in terms of x, the integrals in terms of x. So that's one way of going about it. Then in part B, it says write an integral in terms of y, integrals that gives area, and evaluate it. So notice if we use an integral in terms of y, that would be like this. Horizontal rectangle, where the width is dy. And now notice, unlike the x's, if you look at the horizontal rectangle, it always stays between the same two curves, so there's no need to split it up. And this time when we set up our integral, we'll be using the y-coordinates instead of the x-coordinates, going from the bottom to the top. So notice no matter where you look, the y-coordinate starts at the x-axis here, and the y-coordinate is 0 there, so 0 becomes your lower limit. And as you move up, notice it stops right here when the y coordinate is 2. So it'd be from 0 to 2. And then here we have to go the right minus the left. But remember, they have to be all in terms of y. So we have to do a little more work. I'll do that off to the side here. And solve these both for x in terms of y. Let's start with the one on the right, because that one's going to go first, which is the 7 minus x. So over here, if we solve that for x, all you have to do is add the x to this side and subtract the y from both sides. So you get x equals 7 minus y, so that's going to go first. Oops, that looks like y there. And then minus the one on the left is this one. So this one takes a little more work, but let's go ahead and solve this one for x right down here. So first you would square both sides, and that would give you y squared equals x minus 1. And then add the 1, gives you x equals y squared minus 1. And you're subtracting the whole thing, so in parentheses. And then the whole thing times dy. Alright, then we can simplify it just a little bit here. So the integral from 0 to 2, you can just combine your like terms. So we have a 7, and this becomes minus 1, gives you 6 minus y, and this becomes negative y squared dy. And then we can go ahead and integrate that, each one separately since they're just subtracted. So you integrate 6, you get 6y. Integrate y, you get y squared over 2 minus y cubed over 3. And then this is evaluated from 0 to 2. So when you substitute in the 2, times 6 gives you 12 minus 2 cubed. 2 squared is 4, divided by 2 is 2. Minus 2 cubed is 8 over 3. Minus, when you substitute in 0, it wipes out all of them, so you just get 0. So that's 10. 12 minus 2, which is the same, since it's thirds, as 30 thirds. Minus 8 thirds gives you 22 thirds. So notice we got the same answer, which is what we should get. You don't have to be, this is not specific, but that's what it would be here. So this is two different ways of finding the area. Notice they give you the same answer. So either way is correct, but here it asks us to do it both ways. Sometimes it does as well in the AP test, ask you to find the area, or at least set up the integrals in more than one way. All right. Now let's take a look at another one without calculator, and then we'll look at one that's with the graphing calculator. So this one says, let R be the region in the first quadrant bounded by the graph of y equals 2 cube root of x. So that's this one. The line x equals 8. You can see that's the vertical line right here. And the x-axis right here. Find the area of R. So notice here it doesn't specify. Use a horizontal or vertical rectangle. So if we used a vertical rectangle with dx, notice it always stays between the same two curves. So you wouldn't need to split it up. If you use a horizontal rectangle, also always stays between the same two curves, so you wouldn't need to split it. So either way would be fine. But I'm going to use a vertical rectangle. Just draw one somewhere in here. Because then we won't have to solve these for x in terms of y. We can just leave it. Everything in terms of x. So here the integral would be from, starts at x coordinate of 0 here and stops, this vertical line shows you stop right at 8. And then we'd have the one on the top, which is 2 cube root of x, the same as 2x to the 1/3. And then minus the one on the bottom again is just y equals 0, so minus 0 dx. So now when you integrate that, you get 2 stays there, x to the 4/3 when you add 1 to that, divided by 4/3, the same as multiplying by 3/4. Evaluated from 0 to 8. Then you can simplify that. That's 6/4 reduces to 3/2. And since that's a constant, you can pull out in front. And then put this in radical form. Instead of x to the 4/3, that's a cube root of x to the 4th. So we've got 3/2. And then substitute in the 8. Cube root of 8 is 2 to the 4th is 16. Minus substituting 0 just gives you 0. So then you can simplify that. 2 goes into 16 8 times. 8 times 3 gives you 24. So our area is 24 units squared. Okay, then part B has something a little different. It says there's a vertical line x equals k, divides the region into two regions of equal area. So let's kind of guess where that might be. So look and see where you think the areas might be divided into two regions of equal area. And let's draw a dotted line. About where we think that might be. So maybe I'm just going to guess about right there somewhere. And label that one x equals k. So there's a couple ways you can do this. We could go the integral from 0 to k, and then equals the integral from k to 8. That would work. However, notice we already know the whole area is 24. So that means each of these has to be 12. So what we can do is say integral from, now here we could either go from 0 to k or k to 8. Either way works, but I'm going to go from 0 to k because then we get to substitute in 0, which tends to be easier than substituting in another number like 8. And again, it's just going to be the top one minus the bottom one. So 2x to the 1/3 minus 0, and then times dx. But notice that's almost the exact same integral we just integrated here. The only difference is it's got a k instead of an 8. So we don't have to go through all these steps. We can jump right down to this step here. And the only difference is we're going to be plugging in k instead of 8. So we have 3/2 cube root of x to the 4th. And now we evaluate it from 0 to 8. Or 0 to k, I mean. Oh, and I forgot to put the other side. So the other side of the equation is, I'll just write in general, it's half of the total area, which we got from part A, which was 24. And we saw that simplifies to just be 12. So then what you can do to solve this for, well, first let's substitute in here. So we'll have 3/2. You substitute in the k, so we'd end up with the cube root of k to the 4th, minus when you substitute in 0, it's just 0, equals 12. And then to solve from here, so you could divide by 3/2, but that's the same as multiplying by the reciprocal, 2/3. So then we'll just have the cube root of k to the 4th equals 3 goes into 12 4 times. 4 times 2 is 8. And then get rid of the 4th, take the 4th root of both sides. Now normally when you take an even root of both sides, you would need to put plus or minus. But here we don't have to, because one thing we can tell from the graph is that k is somewhere between 0 and 8. So k can't be negative. It has to be something positive. So the negative answer wouldn't make sense there. So we have And the cube root of, the fourth root of 8 doesn't simplify there at all. And then cube both sides. Get rid of the cube root. So we get k equals. Now you could try to simplify the sum and break it down to the 2's and see how many we can pull out of a fourth root there. Or you could just leave it like this. Fourth root of 8 cubed. All right, now let's go ahead and use our graphing calculators here on the next one. So I'll show both using the TI-84 and the Inspire here. So here it says let R be the region bounded by the line y equals 5. So that's this one right up here. And the graphs of y equals -2 natural log of x and 6 arctangent of x minus 2. So let's go ahead and put those in our calculator. You might know which one is which, but you might not there. So let's start with negatives. So you go y equals on 84, and then -2 natural log is right here next to the 4, and then x, close parentheses, and down, and then the other one was 6 arctangent. Remember on the calculator it looks the same as tangent, then -1, which you get by hitting the second, and then tangent, and then we've got x minus 2. Okay, so now let's change our window size so we can see this. We can kind of tell most of the regions in the first quadrant, a little bit in the fourth quadrant. And I know this is at y equals 5, so window size. Let's make the x minimum -1, so we can still see where the y-axis is, but we don't need to see much of this quadrant. Y maximum, yeah, let's try 6 to start with. At y minimum goes a little bit into the negative part, so I'm going to get -2, and then y maximum, so we can see this where this is up at 6. Graph, there's the first one, -2 natural log of x, the graph's in order. And then there's the 6 arctangent of x minus 2. So let's label which one's which. So this one's y equals -2 natural log of x. And this one is y equals 6 arctangent x minus 2. All right, so it just says find the area of R, this region enclosed by this. So it doesn't specify here whether to use horizontal or vertical again. So let's see, if we use vertical, we could do that. But then notice we'd have to split it right here at this point of intersection because the curve on the top stays the same this time, but the curve on the bottom would be different. So we could do that. And if we did it that way, we'd also need to find 1, 2, 3 points of intersection, find all those x coordinates, which you could do. Or, notice if we use a horizontal rectangle, see how it always stays between the same two curves? So that's going to be a little easier to do on this one. All right, so if we use a horizontal rectangle, then notice we just need to know, if I call this point AB, we just need the y coordinate here, that's where it's going to start. And notice we don't need the y coordinates at these points because we already know it's at 5 because of the horizontal line. So we'll only actually need to find one point of intersection. Let me show you on the Inspire here how we put those in here first. Then we'll find a point of intersection on both graphs. So start a new document, add graphs, and y1 would be -2 natural log. You have to control and then E the x button, natural log of x, and then hit the down arrow. And for F2, we'll have 6 arctangent is on the trig button. Again, it looks like tangent with a -1 of x minus 2. And again, if you want to put 5 in there, you could too, but we don't need that in this case. Then let's look at both calculators for our point of intersection. Go back to the 84 here. And so to find the point of intersection here, you go second calc, and number 5, intersect. First curve just listed right there, y1. Second curve, y2. And guess, just move it using the left and right arrows, just somewhat close to the point of intersection, hit enter. And notice it tells you both coordinates, but we're actually only interested in the y coordinate this time, so I'll write that down, negative 1.177, to be accurate to at least the thousandths place. And then to store it on the 84, you would go second, quit, and then since it's not just the x coordinate, you can't just hit store. It's actually stored in your calculator right now as alpha y, automatically the y coordinate. So if you go alpha, y is on the number 1 there, and then hit store, and then whatever we call it b here, alpha b, and then we could store it right as our y coordinate b. All right, and then on the Inspire, how we do that? We would go menu, analyze graph, intersection, and then lower bound, just move this line to the left of the point of intersection, upper bound, and click, move it to the right and click, and then it gives it to you, and then highlight the y coordinate, and just like we do for the x, var, store, and then choose a letter for it, so B, and it bolds it. And when you write on paper, you have to be at least to the thousandths place accuracy, so now we can write our integral here from b to 5, and then the one we would need first is the one on the right, which is this arctangent. So again, we've got to take this and solve it for x. So let's go ahead and do that. So the first thing you do is to get rid of the 6 out in front. You divide both sides by 6. So you would have y over 6 equals arctangent of x minus 2. Then to get rid of arctangent, you would have to use its inverse, which is tangent. So you would take the tangent of both sides. So we'd have the tangent of y over 6 equals, when you take the arctangent of arctangent, the inverse functions cancel out, so you're just left with what's inside there, x minus 2. And then just add the 2 to that. So you'd have tangent of y over 6, and then plus 2. So that's the one that's going to go first in our integral. That's one to the right. For this to the right has a bigger x coordinate. And then minus, then we have to solve this one. For x to get in terms of y. So again, here you would divide by negative 2 to get the natural log by itself. And then you'd also, make it a little easier, you might want to rewrite natural log as log base e, because that's what it is, of x. So then you can switch it to exponential form. The base is e. The log equals the exponent, so that becomes to the y over negative 2 equals what's inside the log, which is x. So that's what's going to go second. That's the one on the left. So we do minus e to the 1 minus 2 and all times dy. All right, so the last thing we just need to put on our calculator to see what this equals. And notice these, in this case, you can't just use y1 and y2 or f1 and f2 because they're no longer the same thing now that we've solved them. So we could enter them in this way, or since we just have to evaluate the integral, it's easier probably to just type it in. So I'll start back to the 84 again and go second, sorry, not second. Just hit the math button and then number 9, function integrate. And what I want to integrate is tangent. So again, this is what the older 84s and the 83s look like. So tangent, which is right here. On the newer ones, it's going to look like this on the newer 84, so it'll look kind of like the Inspire. So here you put that tangent on the newer ones right here. Older ones here, I'm going to put tangent, and even though just put everywhere there's a y, just put an x. So x divided by 6, close parentheses. Here again, it'll look like this. And then plus 2, then minus, and then you get the e, second e. And if it's an x, for y you put an x, divided by negatives out in front of the 2, so negative in parentheses 2, comma, and then on the newer ones again, you can just go plus 2 minus e x divided by negative 2. And then you put the x here, you put the b here, and the 5 here. Excuse me. And then on the older ones, you have to put the x right here, comma, then your lower limit, which we stored as alpha b, comma, the upper limit, which is 5. Close parentheses and then enter. And we get our area is 11.181. Just again, be accurate to the thousandth place. And then on the Inspire, go dock, insert calculator. Now in the Inspire, you could use X, or on this one, you can really use any variable when you're evaluating an integral, unlike the 84 or 83. So you can do either way. So if you want to use Y, you could put the lower limit as B. We stored it as B. Tab, upper limit 5. We can type it in just like we wrote on paper. Tangent, trig, tangent of y divided by 6. If you don't like that looking that way, you can even put it in a fraction next to the 9 right here. So y divided by 6. Right over to get out of those parentheses. Plus 2 minus e is right here. Make a fraction if you want, to the y divided by negative 2. Again, the whole thing has to be in terms of y, so this would have to be y as well. And you get the same thing. All right, and then part B on this one. Now it says we've got some horizontal line, y equals k, that divides region R into two regions of equal area, similar to the last one, except now it's a horizontal line dividing it. So now, I can draw that about where we think that is. I'll just draw it. Sorry, I'm trying to get to the horizontal dotted line button, but I can't quite get it, so I'll just draw it like this. So wherever you think that is, that's y equals k. And so again, you have the choice here. You could set the integral from b to k equal to the integral from k to 5. Or since we know the whole area, you can just use 1. This is right, but do not solve this one, so we just have to set it up. So I could go b to k or k to 5. Either way, I'm going to go from b to k. And it'll be the exact same thing we had here, the right minus the left. So tangent of y over 6 plus 2 . And then the 5 over 6 plus 2 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 minus e to the y over negative 2 dy equals 1/2 of 11.181, since that was our area of the entire region. Or again, you could say the integral from b to k equal to the integral from k to 5 would also work. This one's just a little less to write down. And that concludes the notes for AP Calculus on the topic of area between curves.